Hey guys, Mr. Marone here. Welcome back. We are going to wrap up G.co.C.11 today, our discussion on quadrilaterals, with just a couple of proofs and then a quick chart to fill in. So if you look at page 16 in your notes, we've got a proof by symmetry and patty paper for the opposite angles of a parallelogram being congruent. We're going to do that one in class, but what I want to look at today is our classic proof, two-column proof of how we can say that the opposite angles in a parallelogram are congruent. So they gave us a parallelogram, and they want us to prove that angle A is congruent to angle C. So just like we've done with all of our other proofs in class, we are going to make sure that we put down here that angle A is congruent to angle C as our target. And what I'm going to just jot down is that when we do this process, if you notice they gave us diagonal BD here. If we wanted to prove that angles B and D were congruent, we could redraw this figure with diagonal AC. So we could say that we're going to repeat with AC to show angle B is congruent to angle D. So I'm going to do one of the proofs. The other proof will be almost identical to it, only we'll have diagonal AC instead of diagonal BD. So the first thing we're going to do, when we have a parallelogram, that tells me that the opposite sides are parallel to each other. So in other words, that AB is parallel to CD, and that AC is parallel to BD. And that's just the definition of a parallelogram. And I use the symbol for parallel to shorten the word parallelogram, just so you guys see the notation there. So once we have that idea of having these parallel lines, what we end up having is that we have parallel lines being cut by a transversal here. We've got these two sets of parallel lines. We've got this transversal coming through. So the first thing we can say is that these two angles inside here, angle ABD, is going to be congruent to angle CDB. And those are alternate interior angles. We can also say the other set of alternate interior angles are congruent. We can say that angle ADB is congruent to angle CBD. And once again, by alternate interior angles. Now, what we've got here are two triangles. So let's try to prove these triangles congruent and then use corresponding parts of congruent triangles being congruent, that reason CPCTC, as our aim. So we need to show that these triangles are congruent. The third piece that we need is the shared side. We can say that BD is congruent to itself by the reflexive property. Okay. And now I've got enough. I've got two sets of angles with a set of sides in between it that I can prove these two triangles congruent. So we can say that triangle ABD is congruent to triangle CDB. And our reason for that is angle, side, angle. We have two sets of congruent angles with a set of sides congruent in between it. And then, as I said, we can then say that the two opposite angles, angle A and C, are congruent by CPCTC. Now, if we just replaced diagonal BD with diagonal AC, the same exact process would exist. Now let's take a look at the second proof that we've got in our notes for this section. And that the proof that we're aiming to show is that we've got diagonals being bisected here in a parallelogram. Okay, so our ultimate goal is to show that DE is congruent to BE and that CE is congruent to AE. That's our ultimate goal at the end of this proof. And once again, if you can tell in this picture, we've got some triangles to deal with, so we're going to work through a bit of a triangle proof and try to use CPCTC at the end to show that these segments are congruent to each other. First thing we're going to do, just like our last proof, we're going to use what we know about parallelograms and say that that side AB is parallel to CD and that side AC is parallel to BD. And once again, that is the definition of a parallelogram. Okay. From there, we've got a couple sets of alternate interior angles here. Okay, we've got angle CDE, this angle here, and its angle across from it, angle ABE. So angle CDE is congruent to angle ABE, and we said those are alternate interior angles, much like our last problem. And we've also got a set angle DCE is congruent, so here's DCE right there, and that's going to be congruent to angle BAE, once again by alternate interior angles. And one thing that we've got here, if we want to show that these two triangles are congruent, since we don't really know anything about either diagonal, we can use the sides of a parallelogram. We know that in parallelograms, the opposite sides are congruent. So in this case, that helps because I've got that side AB is congruent to side CD, because opposite parallelogram sides are congruent. Now I have enough information to show that triangle ABE is congruent to triangle CDE. I've got two sets of angles with a set of sides congruent in between it, so I can say these are congruent by angle side angle. And once we have triangle congruence, we can say that any corresponding part is congruent because of those congruent triangles. So we can use CPCTC to wrap up our proof for that one. So we've got our two proofs done. The last thing we need to do is to fill in our chart on the next page, on page 18 of our notes. Okay, there's two parts to it. One is this big chart here that allows us to fill in all the different properties, much like we did yesterday. So real quick, we're going to run down and just put check marks by all of these different things. And I'm going to start with the parallelogram theorems and fill in everything from there, since we know that rectangles, rhombuses, and squares all match what a parallelogram has. So in a parallelogram, opposite sides are parallel. That's going to be true of all of them. Opposite sides are also congruent in a parallelogram, which will be true for all of them. The opposite angles are congruent, and the consecutive angles we said were supplementary. So those four are all true about parallelograms. Four congruent angles only exist in two figures. They exist in the rectangle and they exist in the square. Four congruent sides only exist in the rhombus and the square. In all of these, the diagonals bisect each other. We just proved that on the last page. The diagonals are congruent only in a rectangle and a square, but the diagonals are bisectors in the rhombus and the square, and they're also perpendicular in the rhombus and the square. So those are all the different facts that we've learned about parallelograms and those other figures that fit under the parallelogram umbrella. The last thing we want to do is take this Venn diagram. We're going to draw a picture here to show what all quadrilaterals, where they fit into when we have special cases. Okay, so the biggest set of them that we've looked at were the parallelograms. And within that, we have the rhombus and the rectangle, and they combined to create the square. So we're going to create kind of a classic looking Venn diagram here, where I've got the rhombus, I've got the rectangle, and then in between them is the square. Right? That shared set would give us the square. We then have those outside figures. If you look in our directions, they want us to discuss the trapezoid. That's another figure, but does fit under the quadrilateral umbrella. So it's got its own grouping. And there is another figure, a sixth figure, that we haven't really talked about much, but does fit in here, and that is the kite. So we'll put in its grouping as well. So that is how all the relationships fit within our quadrilaterals. I encourage you to try the homework problems tonight to see if you can continue to apply all of these various truths that we now have, or different properties. So what we're going to do is let you practice those, and if you have any questions, feel free to bring them into class tomorrow.